So we're very pleased to have for our colloquium today Mark Mclean from University of Aberdeen, who will talk about the symplectic geometry of Stein manifolds and affine varieties.
Okay, so I will explain. So what I will do is in this title there's three words, so three things: symplectic geometry, Stein manifolds, and affine varieties. So I'll explain symplectic geometry first, and then I'll talk a little bit about Stein manifolds, affine varieties, and some of the background, and then we'll go on from there to my results, in these areas. So I'll start with Hamiltonian Dynamics and sort of how this gives us the definition of a symplectic manifold, and then I'll give some examples of symplectic manifolds, so cotangent bundles, smooth affine varieties, and Stein manifolds, and then I'll explain some theorems relating some of these objects, so relating cotangent bundles with smooth affine varieties and Stein manifolds, and sort of putting all of this together. Okay. So I'm going to start with Hamiltonian Dynamics, so this is where it all started. Okay. So we have some physical system, and it has some position coordinates and some momentum coordinates. So it could be, I don't know, some particles in space doing something. And this system can be described at any one time. You can, if it's a classical system, it's a nice system, with its position and its momentum, you can describe, quite often you can describe what its energy is at that point. So its energy is given by some function of these coordinates. So in this case it's called the Hamiltonian, it's h of q1 to qn, p1 to pn. So at any one point you have some energy in the system. And from this information, so from these coordinates and from this function h, which we call the Hamiltonian, we can construct a path of the system. So we have a starting point, which we just choose, which is sort of at time 0, it would be q1 to qn at time 0, and p1 to pn at time 0. So that's where it starts. And then it satisfies a first order ordinary differential equation given by these things here. So it's partial derivatives of the Hamiltonian are on the left, and time derivatives of the coordinates on the right-hand side. And it's a first order equation. So in symplectic geometry, we're really interested in not writing these equations quite like this. We prefer to write them like this. So they're the same equations, but they have a vector on the left given by the partial derivatives of the Hamiltonian, and a vector on the right given by the time derivatives of the coordinates of our system. And then there's this matrix in the middle. So somehow symplectic geometry is, we're really interested in this matrix here, somehow, in some sense. I mean, we're also interested in the Hamiltonian system as well, but okay. So I'm going to give a basic example, and it's very basic. So it's just a bead on a wire. So it's a smooth bead on a wire. So the wire is, I'm going to just assume, is frictionless, and the bead will just go up and down the wire. And you can track. So it has one q coordinate and one p coordinate. So the q coordinate is how far it is from the horizontal middle, and the p coordinate is how fast it is going horizontally, and that gives you all the information about the system anyway. So, and so you can plot on the right-hand side what the bead does, and it's just a phase space diagram, and here's a silly animation showing this. So really we consider all the systems all at once. All the different initial conditions all at once on this wire, and we see what happens on the phase space diagram here. And you can see that these beads on this side, they're rotating uniformly around. So the point of describing a system on the right-hand side is that you see symmetries of the system that you wouldn't necessarily see on the left-hand side, which is, I think, one of the powerful ideas of behind Hamilton. A powerful.
So this is just gravity, or what's going on?
That's gravity. So
Okay.
yeah, it's gravity and it's all frictions.
With no friction.
Yeah, it's. Okay, so back to the presentation. Okay.
So the phase space is better, therefore symplectic things are better, right?
Yes. But the downside is we don't have friction, which some
Right.
engineers wouldn't like.
Right.
So, which is a problem. Okay, so what is a symplectic manifold? Well, so I have this sort of rough definition here. So it's a manifold with a two-form which locally looks like this matrix, and this is exactly the same matrix that was in the equations before. And so there's an equivalent way of defining this, which is it's just a manifold with a closed non-degenerate two-form, and that's the sort of slick definition. I mean, another way of describing it is, well, you have these Hamilton's equations. So on the left you have partial derivatives of the Hamiltonian, and on the right you have time derivatives, and you have this matrix. And if I just change the coordinates, so I change the p's and q's to some other p and q coordinates, and I look at what the structure of the equation does, it changes. You get a different Hamiltonian on the left-hand side, and you get it's equal to some new matrix times time derivatives on the right-hand side. And so if those coordinate transformations sort of preserve this matrix, then that's a sort of nice change in coordinates. So you can imagine a symplectic manifold as sort of like a topological space, and each we have these sort of charts which locally look like these sort of phase spaces, and they overlap by these nice changes of coordinates which preserve the structure of this equation. Okay. Okay, so here's a sort of slightly more non-trivial example. So we have some manifold, and we can construct its cotangent bundle. So what you should think of is, again, a sort of one way of thinking about it is as a bead constrained to that manifold. So this is an example given by where the bead is constrained to a circle here. And then its cotangent bundle is given by a cylinder. So you have the circle, and I've just flipped the circle so that it's on its side like this. And then the height of the cylinder represents the momentum. So again, the motion of the bead will trace out some path here. And if I had a nice animation, there are actually some really nice YouTube animations, which I'm not going to show you, but there's some really nice animations where you can sort of, so the equivalent of the animation I showed you before, where you have a sort of nice flow and these nice sort of patterns and things like this. So you can sort of see symmetries and sort of features of the topology of this cylinder sort of reflected in the system. So that's the example of cotangent bundles. So the next examples we will look at. So another example. So here's just another picture. So you have a bead constrained to other manifolds, like a genus 2 surface or something like this. And that's just a picture explaining not very much. Okay. So smooth affine varieties. So these are very different symplectic manifolds. I don't really have a sort of nice bead on a wire description of them, but they're described in a sort of algebraic way. So you take some polynomials in complex numbers, and you look at the zero locus of those polynomials, and you choose the zero locus, and so you want the zero locus to be in such a way that it's a smooth, complex manifold. And if you can do that, then you can restrict the symplectic structure on Cn to the complex manifold. So the point is that Cn has these p coordinates and q coordinates, So if you look at sort of z, if you look at the j, z coordinates, z coordinates of Cn, then you can think of it as sort of pj plus I times qj, or it's the other way around, qj plus I times pj. And using those coordinates in that standard symplectic form, we can sort of restrict it to this submanifold and study. So we view this affine variety as a real C-infinity manifold with a symplectic form on it. And so here's some examples. So the first example is given by this equation, and it turns out that this is symplectomorphic to the cotangent bundle of the two-sphere. And then there's another example here where it's symplectomorphic to the cotangent bundle of the torus. And then there's this one here, which this is a polynomial. So if you write this out, it's divisible by z3, so you can divide out by z3. And this has nothing to do with cotangent bundles, not homotopic to a cotangent bundle or anything like that. So well, unless it's a point, it's not a point. So these are some examples of smooth affine varieties. So there's a more general thing that both smooth affine varieties and Stein manifolds sort of come on. So there's a more general version of a symplectic manifold called a Stein manifold, which basically is sort of like, in some sense, it's a sort of analytic equivalent of an affine variety. And it's a nice, properly embedded complex submanifold of Cn, and you restrict the standard symplectic form of Cn to this nice submanifold, properly embedded submanifold. And then you get an example of a Stein manifold. So they're both examples of Stein manifolds. Okay. So the next part of the talk, I'm going to explain some results which sort of show the relationship between sort of symplectic topology of Stein manifolds and sort of the relationship between the symplectic topology of Stein manifolds and the actual sort of topology and how this plays out.
Do you need to assume the base of cotangent bundle to satisfy some condition for it to be Stein? For any?
So it turns out that for any cotangent bundle of a compact manifold, it is symplectomorphic to a Stein manifold.
So any real analytic manifold has to be complexified as a Stein manifold, and so you can, and then the resulting manifold is, you can actually think of it as the cotangent bundle. So you can always find a
the sphere, for example, for the sphere.
Yes.
So just take the same equation and make the
Oh.
So if you look at, let me go back to here. If you think of this as x1 squared plus x2 squared plus x3 squared equals 1, that's in real coordinates. And then you complexify it. So then you can think that the cotangent bundle is when you complexify it. And then you have to look, in general, you have to look at a small neighborhood of the real locus. So you can't look at the whole equation. You just have to look at a small neighborhood of the real locus and you get something Stein. But it's definitely not affine in general. So I'm actually going to explain more of that in a minute. So this is why I was explaining these examples here. Okay, so some questions about Stein manifolds. So these are some of the questions that I've been interested in personally. And that many other people in my field have as well. So they're sort of open, they're sort of very vaguely worded questions. But, so what are good ways of describing Stein manifolds symplectically? Is there some say, topological way of describing these things, or is there some sort of combinatorial way of describing these things? Sort of in a sort of up to symplectomorphism, so up to an equivalence of preserving the symplectic structure. So the next one is, what is the relationship between the sort of algebraic and analytic properties and the symplectic structure? So, like for instance, if you have an affine variety, it's an algebraic object, so it has various algebraic properties. and you want to think, well, what does if I just forget if I look at just the symplectic structure, what sort of properties can I sort of extract? What sort of properties of the affine variety can be obtained from this symplectic form? And so some like nice relationship between the two things. And then there's sort of dynamical questions, which I'm not really going to cover in this talk, which are, if I have a Hamiltonian system on, say, this affine variety or on the Stein manifold, what can I say about it? Symplectic geometers have been interested a lot in one-period orbits of a system, so how many initial conditions are there, so that after time one, I come back to where I started again. So for instance, in that picture I had, there were millions of one-periodic orbits, because all of those beads came back to where they started again. But in general, that's not going to happen.
So you're restricting the linear symplectic structure on Cn to the variety?
Yes. And then there's mirror symmetry questions, which I don't know as much about, but there's lots of people working on this, especially for affine varieties. There's a very nice story going on. And it's actually relevant to some of the tools I use. Okay, so as I said, I'm actually going to focus on these two questions here. So what are good ways of describing them, and then the relationship between the algebraic and analytic properties. And I'm going to sort of split the rest of the talk, I hope, in two, going through these questions. Okay.
Well, there are three things: affine variety properties, and symplectic properties, and the relationship between.
Yes.
You said you were split into two.
I'm going to split. Well, I'm going to sort of split along here, but I suppose these questions are sort of joined together a bit as well and things. So it's a bit. There's no precise cut. Okay, so let's have a look. Okay, so here's a result by Weinstein, which says, so every Stein manifold has an explicit handle decomposition, and each handle has an explicit symplectic structure on it. So I'm not good. So I'll explain the complex one-dimensional example, which is real two-dimensional, which is here. So this is describing Stein manifolds up to symplectic morphism. So what do? I take a disk, and I have, say, for instance, some marked points on the boundary, which I've labeled sort of in pairs, and then I attach handles along there. So this gives me a manifold, a real manifold with boundary. So it looks like the once-punctured torus. Well, the torus with one boundary. And then I want to make it into something symplectomorphic to a Stein manifold, but a Stein manifold doesn't have as viewed as a real manifold, it doesn't have a boundary at all. It's just, so how do I get rid of this boundary? Well, what I do is I just attach an infinite cylinder, and I just glue it on here. And then I put a symplectic form. I need to put a symplectic form on this. So in this case, I just have the standard, the symplectic form is a two form, and so it's just a volume form on here. So I just have some volume form on here. And here I have this sort of cylindrical volume form, and I just glue them together on here, and I get something, I get, just draw it glued together. Something like this, with a volume form, sort of infinite, giving it infinite volume. And this gives me a Stein manifold. It's symplectomorphic to a theorem. It turns out that it turns out that this is actually symplectomorphic to some Stein manifold, which is a once-punctured elliptic curve. Okay. And then there's this two-dimensional example, which some people in this room will understand, maybe some symplectic geometers, but I don't expect anyone else to. But sort of, you have these ones and twos suggest that this is the equivalent of attaching these handles, and then there's these lines, which are sort of two handles, but they have cusps, which sort of explain how the extra structure comes in to the handle Okay. Okay. So what else can we say about Stein manifolds? Well, the first theorem is a result by Eliashberg, which says if you have two diffeomorphic Stein manifolds, and this diffeomorphism satisfies an additional topological condition, then if you cross them with C, then this becomes then you can deform it so it becomes a symplectomorphism.
C is complex.
C is a complex, yeah. So C is the complex thing. Yeah.
R2.
Yeah, exactly. So you think of C as R2 with the standard symplectic form. You take the product symplectic form. And so this theorem of Eliashberg says that if you take Stein manifolds and you cross them with C, then suddenly the problem becomes a topological problem. So there's topological constraints on how there's only topological constraints to telling you when two things are say symplectomorphic to each other, and so on. And so you might think, well, is Stein geometry a purely symplectic problem? So I mean, a purely topological problem. Can I boil everything down to just topology? And the answer is, well, no. The answer is no. So Paul Seidel and Ivan Smith said that there are at least two symplectomorphic smooth affine varieties, and they're both diffeomorphic to R to the 2n, but they're not symplectomorphic. So that means that this is definitely not a topological problem.
What distinguishes them?
What distinguishes them? So, well, the first one is just standard Cn. And then the second one admits a special Lagrangian torus, which is non-displaceable. And they use Flower Homology invariants to do that. So,
The compact torus.
yes.
Is it easy to say what the extra condition on A and B is in the first theorem?
Yeah, so it's they both have complex structures, and you view them as almost complex structures, and then they need a whole topic. Okay, so this is my addition to the theorem of Seidel and Smith, which is that there are infinitely many pairwise non-symplectomorphic smooth affine varieties. So there's an infinite family of smooth affine varieties, and they're all diffeomorphic, but they're all pairwise not symplectomorphic to each other. But the proof is also very different. I use a completely different invariant called symplectic cohomology to deal with this. And I'm going to explain a bit about that a bit later, though I'm not going to really use the word symplectic cohomology.
So, for example, in these examples in the second theorem, they all do have the property that they're state. When you cross by C, they're all symplectically the same. There's no invariant.
Yeah, exactly. Yes. So.
Well, they satisfy the topological condition.
Yes, because they're all contractible.
Oh, that's true.
So when you classify construction of
Okay. Okay. So you might ask, well, is there some sort of recipe for telling you whether two Stein manifolds are the same or not? So if I give you, say, these Weinstein-Handel presentations, is there some way of saying whether they give you symplectomorphic Stein manifolds? And again, the answer is no. If I have two very explicit Weinstein-Handel presentations, sort of these diagrams, then there's no algorithm. If I feed those into a computer, there's no way that my computer could tell in general whether two of these things are symplectomorphic or not. So the point is, the way this sort of works is, for you, as with lots of these sort of non-computability things in geometry, you boil it down to a problem called the group word problem. So you take a finite presentation of a group and you sort of build one of these Stein manifolds from it, and in such a way that they're all diffeomorphic, and then you get some invariant to sort of remember enough of the presentation so that you get an undecidability result. But this was also done.
You think of transition groups as being like one handles and two handles, so somehow the symplectic structure allows you to get down to
So what I do, what you do is so you start with something like a cotangent bundle, and you start with the undecidability result for normal manifolds, and then you take their cotangent bundles, and then you sort of kill all their topology somehow. But without changing, but in such a way that the symplectic structure remembers it, so the invariants you're using still remember that the part of the fundamental group that you're killing.
So you cancel each handle on the level of the dimorphism, but it doesn't.
Yes, but somehow the handles are built in such a way that it still remembers the symplectic structure. So Paul Seidel did this earlier, and then I did it for everything diffeomorphic to constant 2. Okay, so you might think, well, that makes this subject very hard to study because, I mean, once you have an undecidability problem, you can't study things in general, but obviously people don't give up and have something undecidable. So it's best. So what we do is we look at, say, more specific objects and sort of study those. So this is sort of what brought me to studying affine varieties, because I feel as though they're much more computable. So this is the next result. So the next result is...
Well, among affine varieties, it should be decidable, shouldn't it?
Yes, probably, yes.
Right. By Tarski.
Well, you would hope so, but I don't know.
Okay.
I don't really know. When you think you go up to symplectic morphism, I have no idea, but I suspect you're right. So we had these two basic objects at the start of this talk, which were cotangent bundles and smooth affine varieties. And these are these sort of basic objects. So the cotangent bundles were these beads on these manifolds, and then you have these sort of zero sets of complex polynomials. So I say that most cotangent bundles are not symplectic morphic to smooth affine varieties. So most means when the cotangent bundle is sufficiently complicated topologically. So, for instance, if the fundamental group grows very fast, or if you take a manifold with trivial fundamental group and you look at the sum of the beta numbers, and the sum of the beta numbers is sufficiently large, then they're not symplectic morphic. So here are some pictures. So earlier in the talk, I gave you some examples of affine varieties, and both of those were turn out to be turns out to be symplectic morphic to the cotangent bundle of the 2-sphere, and the other one the cotangent bundle of the torus. But if I take a genus 2 or higher surface, then that cotangent bundle, that phase space associated to this bead here, it's never symplectic morphic to any affine variety. So there's no way of sort of modeling the system in terms of polynomials and complex coefficients.
What's the idea of that?
What's the idea? So I'm going to explain that.
Okay.
So I'm going to explain the tools behind this. So the idea is to do with the tool is called growth rate of symplectic homology. That's its full long name. So I'm just going to call it growth rate, and it uses a tool called in symplectic geometry called Hamiltonian Flower Homology. So I'm going to explain this very quickly, and just some of the sort of ideas behind this. Oh, but before I do that, I forgot about this slide. So I wanted to explain how this relates to another problem in algebraic geometry, I think. So if I take some manifold Q, and I describe it as the zero set of some polynomials with real coefficients and real numbers. So I describe it in terms of some k polynomials, zero set of k polynomials, p1 to pk, in a smooth way. And then I take these coordinates x1 to xn, and I complexify them. I replace them with z1 to zn. And I look at the resulting affine variety here, so Q, which I call Q of C.
So you're assuming that Q is actually still smooth, it might not be.
Yeah, I'm assuming Q is still smooth. Yes. And then you can ask, so this set here is naturally included into this set here. So you can ask, is this inclusion homotopy equivalence? And so there's various results and conjectures about this. So for instance, Kulkarni proved that if it's a homotopy equivalence, then Q has a non-negative Euler characteristic. And I think there's a conjecture by Bert-Taro which says, again, sort of, as I said before, if Q is sufficiently complicated, then you can never present, there's never a homotopy equivalence. So it's sort of, there's some sort of relationship between these two things, this symplectic result and these complexifications of polynomials, but I don't know a rigorous connection between them, but there's some sort of analogy going on. And this is what actually motivated me to do this problem in the first place. Okay, so I'm going to explain why my theorem is true now. Okay, so the main tool is called the growth rate of symplectic cohomology. So this is just an invariant of the Stein manifold up to symplectomorphism. And it's a number, and, well, it can be minus infinity or any positive number, or plus infinity. And then there's two theorems. So the first one says if I have a smooth affine variety, then this growth rate has an upper bound given by the dimension of A, the complex dimension of A. And then there's a theorem by this proved by loads and loads of people in different ways. So Aberdeen Schwartz did one way, and Simon Wader did another way, and Viterbo was the first person to do it. He did it in the third way. And they showed that if you have these sufficiently complicated compact manifolds, then the growth rate is plus infinity. So they related this to an explicit sort of topological thing in terms of the loop space of manifolds. Okay, so what I will do is explain this part. Well, I'll explain what growth rate is, basically, and maybe one sentence about this theorem. So what is growth rate? So if I'm given a symplectic manifold and a Hamiltonian has to be nice, but I don't want to say anything about that, then I have a
nice near infinity.
Nice near infinity and sufficiently generic.
Quadratic growth or something like
yeah.
that. Like it is in the cotangent model.
Yes, exactly. So I will actually explain that in the next slide as well. So I have just for the moment I just have some symplectic manifold and a Hamiltonian, and it's sort of nice in some way. Then I can get this group called the Flower Homology of H. And so what is the Flower Homology? Well, it's a homology theory, so you need a chain complex and a differential. So the chain complex is the following thing. It's freely generated by fixed points of this time one Hamiltonian flow. So what does that mean? It means I have my Hamiltonian system. So remember I had like all these, for instance, all these beads flowing everywhere on this thing. And I want to look at the number of points where if I start my bead at that point, it goes back, and after time one, it comes back to where it started again. And I count. I take the free complex generated by those things.
What's the grading?
Well, the grading is called the Conley-Zander index. And it's
Not related to the twist or something?
it's related to, it's sort of related to this. If you look at the sort of linearization of the flow and how it twists around.
The number of twists, maybe.
Yeah. You need to choose a sort of trivializations to see the twist. So it's a bit of a long story. That's basically it. And then you have a differential. So the differential. So these fixed points, you can think of them as sort of solutions of some ODE with endpoint conditions. And then you have a differential, and that's some count of some solution of P, some sort of PD, which I won't really explain. But So the differential is given by a matrix, and the matrix, each entry is a count of the solutions of some PDE called the perturbed Cauchy-Riemann equations. So this start bit here looks like the Cauchy-Riemann equations, and this is a sort of perturbation of it. So this is an extremely powerful tool in symplectic geometry, and it's used to prove many, many things. Okay. So what's the growth rate? So if I have a Stein manifold, I can choose some Hamiltonian given by the distance squared from the origin, Cn. So, I can calculate its Flower homology group, and the growth rate is roughly the rate at which the rank of this grows. It's not quite true, but it's close enough. So,
is it like the power of the lambda to the n, like it's polynomial degree n, and the n is the growth rate?
Yes.
And if it's anything higher than polynomials,
So I'll actually say that now. So if it's a polynomial, then if it's a polynomial of degree k, then the growth rate is k. And if it's 0, if these groups are 0 all the time, which can happen, then I define it to be minus infinity. If it grows exponentially, then it's plus infinity.
but if it grow like e to the square root of n, it would still be plus infinity.
Yes.
Like the partitions, which occurs in examples.
Yes.
That has 0 growth, exponential growth rate. That example. So you're thinking it'd be infinity equal to the 0 exponential growth rate.
Right. But e to the root n is kind of interesting because I think you can still sort of, even though growth rate's a number, you can still, I don't know if you can, I'm not sure. Maybe, anyway.
Yes.
Is the growth rate in general a real number, or is there always an integer if it's finite?
So the way I described it, I suspect, I only know integer examples, but there's another growth rate in Flower homology called the growth rate of rat Flower homology, which is another version of this growth rate. And then in that case, it can be transcendental number. So I suspect this really has something.
But you're just taking the lim sup of log of the...
Yeah. Okay. So how do I so the good thing about growth rate is I can easily construct, well not easily, but fairly easily, relatively easily construct upper bounds for the growth rate. So remember that Hamiltonian flow homology, you had this chain complex and you had this differential. The differential is really hard to calculate, but the chain complex part, the actual chain complex is a vector space without the differential. It's much easier to calculate. So you can easily get upper bounds by sort of bounding the sort of size of the chain complex itself. And that's what I do for these affine varieties. I choose some very nice sort of, I make sure my Hamiltonian looks very nice, and I sort of count. I just put an upper bound explicitly on a number of sort of these one periodic orbits. And this gives me my upper bound of the growth rate by a polynomial of degree, the dimension of A. So that's how I do it. So I wanted to explain another sort of side of this other question, really, which is the sort of relationship between the algebraic properties of an affine variety and the symplectic properties. So this is another sort of this is a different result. So I'm going to explain an algebraic invariant of an affine variety. So what I do is I take my affine variety and I compactify it somehow by some projective variety x. So I compactify it in some way. So, and then I look at the and then what I do is this compactification is a nice smooth complex manifold, and what I do is I look at the following thing. I look at so if you have a complex manifold, you have the canonical bundle, which is the highest exterior power of the tangent bundle, and you look at the number of sort of the space of polymorphic sections of this thing with poles. So if that might not make sense to some people, so it's just some algebraic invariants. Otherwise, you didn't get what I said there. So, but I'm counting sort of holomorphic things, holomorphic sections with a pole at infinity. And I'm looking at it. I'm looking at the rate at which this grows.
So here, I guess, a priori, you could have more than one compactification, but you have the same
yes,
relative.
Exactly. Yeah. And I should also say, even though I said rate at which something grows, this has nothing to do with the growth rates I said earlier.
So you don't have to carefully define the minimal resolution in the projective space or something.
No, just take any resolution, and then you look at the sort of the sort of ranks of these vector spaces, and you just look at how high they grow. And that's called an important invariant called log.
Well, why does it depend on the compactification?
So
it's a bipolar. I don't know.
Okay, it's because bipolar. I mean, if I choose a different compactification, it's biholomorph. So they're both biholomorph. Birational. So. Okay, so this is a theorem. So log Kodaira dimension is a symplectic invariant. If I look at smooth affine varieties of dimension 2, and they have to be acyclic, so that means the homology of the variety has to be the homology of a point. So that's a bit restrictive, but I hope that it's not like one can get rid of that maybe. In particular, it also means that the symplectic form is actually a biholomorphic invariant, so it also proves that it's a biholomorphic invariant, although actually people have probably proved that in the past. But this is a sort of symplectic result. And then I have partial results in dimension 3. So there's a large family of three-dimensional affine varieties. And I can't prove invariance, but I can prove sort of if one is symplectomorphic to the other, then there's certain restrictions in what the log Kodaira dimension can be. And they're definitely not just sort of smooth restrictions. It's definitely dependent on symplectic form. And then there's a sort of work in progress. Again, there's some sort of result in all dimensions. So it's sort of positive versus non-positive log Kodaira dimension. And that has a slightly different proof, and but it's work in progress. And I hope to finish that sometime.
In dimension 2, is it a diffeomorphism invariant or compactification relative to the divisor?
I don't know.
Because it's certainly if you have four manifolds, the Cyber width theory determines what the usual Kodaira dimension is. So
I wouldn't be surprised, but I don't actually know. I didn't thought about that. What I should say though is that these symplectomorphisms can behave extremely horribly at infinity. There's no way the compactifications can be very different. For instance, so remember there's this result by Eliashberg which says A times C B times C if there's so these can have the A's and B's can have very, very different compactifications, but they're still symplectomorphic. Still symplectomorphic. Symplectomorphism is still very
right, but in this case, it'd be related to the fact that you lose most of four-dimensional differential topology when you cross
yes.
by R.
So. But it's also interesting that the log Kodaira dimension of both of these are minus infinity, so it sort of fits very well with Eliashberg's result. Okay. So here's another condition. So I know some people in this group do study use the Russian curves and varieties. So you can ask sort of, so there's this result by Ruan and also Collar, which says if I have two projective varieties, then sort of being uniruled, which means there's a rational curve for every point. Non-trivial one is a symplectic invariant. And so you can ask the same for affine varieties. So supposing I have an affine variety A, and it has a non-trivial rational curve passing through any point. So
you can't confuse the audience. So the statement is that given a point, there's a rational curve through it. Right?
Yes. So maybe I'll write this down. So I'll write this down. So you can phrase it like this. So for every point P in A, there exists a holomorphic map, well, I mean algebraic map, Raven's algebraic map. From C minus some points to A passing through this point. So that's what it means to be uniruled. So for instance, again, silly example is if I took sort of A times C, that's uniruled because any point in here, there's a C corresponding to this C passing through each point. So that's a silly example. But I could do other things, like I could take...
That one really is ruled.
That's ruled, yes.
Yeah, that's really ruled.
Yes. Yeah. You can have things that are not ruled.
It's not ruled.
Rational curve.
So, actually, another way of phrasing this is that if I have two sort of projective varieties, and I mean, being uniruled is by rational invariance. So, if I have two projective varieties and they share a common affine set, then one is uniruled if and only if the other one is uniruled. And this is sort of like a strengthening of that in some sense. Okay. So the methods to prove these two results are slightly different. They use Gromov-Witten invariants. So the thing is, Gromov-Witten invariants involve compact things, but these are open things. So what we do is we compactify them appropriately, and then we look at Gromov-Witten invariants on it. So I think I have a sentence or two saying something about that. So what we do is we take our affine variety A, and we embed it as an open subset, a nice affine open subset of the projective variety. And then we look at P1s, so maps from P1 into X, holomorphic maps, and we sort of count them. And we relate these counts to Locadaro dimension. And again, this uniruledness result, you sort of translate uniruledness result into some sort of Gromov-Witten count P1s, and then you sort of
Non-singular projective, right?
they're non-singular. This is non-singular and exactly. Yeah, so I missed that. Okay. So
Sorry, can you explain a little bit of how to relate the Locadaro dimension with Gromov-Witten invariant?
oh yes, sure. So maybe I'll look at it in the affine surface case, so supposing I have one of these acyclic affine surfaces, and it is supposing it has Locadaro dimension 1, and I want to show that another affine surface symplectomorphic to it has the same Locadaro dimension or something like that, or maybe the same or less, or something like that. Then what you can do is you have this affine surface A, and then you show that it has a nice, say, map to some other curve or something like that. Generic fiber is C star. So it's fiber is C star. Generic fiber. Like this. And then what you do is you compactify A and sort of extend this map to this compactification. And then you have a sort of P1 vibration. And then you're looking at map. You want to remember the sort of fibers of that map using Gromov-Witten invariants. And so what you do is if you have some B, let's say symplectomorphic, there's another affine variety B and it's symplectomorphic to A, then what we want to do is show that B also has a sort of C star for each. You want to show that B has a C star for each point and use this kind of degeneration technique to do this. That's a bit complicated. Does that make any sense? I don't know if that makes any sense, but it's a sort of strategy. So,
to prove some invariant is non-zero, to prove.
Sorry?
To prove Gromov-Witten invariant is non-zero?
Yeah. So you show that some Gromov-Witten invariant for compactification is non-zero, and then use the fact that it's non-zero to sort of show that B has a C star for each point, and then relate that to log Godard dimension.
And you're only using the log Godard dimension that happens between the B as target vibrations?
Yes. Okay, so I just have this is my last slide, so I'll just explain a bit about further directions and some of the sort of projects that I want to carry on with. So you can ask sort of what other algebraic structures are remembered by this symplectic structure. So one is rational connectedness. Rational connectedness says, well, it's the same thing, but instead of for every point, you have for every 2 points, there is a curve passing through these 2 points. And you can ask, is this a symplectic invariant? And I don't quite know how to prove the result about this. This is very hard. I mean, even with projective varieties, it's incredibly hard. And I think you can prove something here, and that was a very good result. I think the result is the result is false for affine varieties. And the reason why I think it's false is, again, it's this result by Eliashberg, which says if A is diffeomorphic to B with a topological condition, then A times C is symplectomorphic to B times C. So what you do is you sort of show that these A's, one of these A's is, say, uniruled and like rationally connected, and the other one has, say, very not rationally connected. But they're diffeomorphic, and then you show they're symplectomorphic by crossing with C. So somehow, in the affine case, this rational connectedness sort of thing is probably false. So I would like to know what example. I thought of had an example, but maybe some help me sometime with that. And then, so I have another question which says, what about log general type affine varieties? So what does that mean? So log general type means the log Godard dimension is very high. It's the highest possible number you can get, which is the dimension of the variety itself. And I think that somehow, when it's very high, somehow more of the algebraic structure is remembered by the symplectic structure. And so I have sort of various ideas for instance, how, if you have a sort of sufficiently sort of minimal, say, compactification, how the symplectic structure could sort of remember parts of that compactification, which would be completely false if the log Godard dimension is very small. And then there's a second question, which is actually related to some of these other things, which is the relationship between dynamical and algebraic properties of affine varieties, which are, I feel as though, again, these sort of log Godard dimension things sort of tell you that these Hamiltonian dynamics are sort of different somehow, sort of reflected in this structure. And this last question, what can I say about singularities? So this is kind of different, and I don't really have time to explain this very much. But so I've been looking at, say, smooth affine varieties, but you can also look at zero sets of complex polynomials where you have some sort of isolated singularity like this. So it's a schematic picture. And then you can look at the length of the singularity, which is a sphere like this, and you intersect it here. And this is naturally something called a contact manifold, which is also very natural in symplectic geometry. And there's some very nice. So some of these tools, I feel as though we can study this in sort of. So lots of people have studied these kinds of things in complex dimension too, but sort of in higher dimensions, less has been done. And I feel some of these tools used to prove these results would be appropriate in this setting. That's probably what I would say. And I would probably stop here. Just
Are there any further questions?
Further questions?
We'll go over there.
What's the second topic? What did you say there?
It's the relationship between dynamical properties and algebraic properties.
No, I can read it. Yeah. What did it say?
So, well, this isn't really a concrete project, but it was sort of. I wanted to sort of. I wanted to prove for affine varieties with log general type. I wanted to prove sort of dynamical results about. So if I took a log general type thing and I intersect it with a very large sphere, I get a contact manifold. And you can look at the sort of rave dynamics of this contact manifold. And I feel as though sort of when it's log general type, the rave dynamics. Generally, I think when it's sort of when it's log general type, there gets lots of say grade orbits with sort of a negative index, and also it's sort of they behave in such a way that quite often you get infinitely many of these grade orbits all the time for any contact structure, any contact form, so any rate flow, and so I feel as though this is sort of the dynamics is very you get loads and loads of orbits, and I feel as though some get interesting dynamics there.
I mean, the rate thing is like the boundary effect of the symplectic structure inside.
Yes.
And the flow lines there, is there anything that sort of fills in the flow lines inside? Like some kind of generalized J-homomorphic curves?
I feel as though the thing is, because it's log general type, there's actually fewer curves that sort of go into the interior or something like this. So I actually.
Compact.
Yeah, it's.
Compact curves.
Sorry for.
Fewer compact curves? Or?
Yeah, fewer. I mean, if you view. I mean, the other way of thinking of it is. Yeah, fewer compact curves. So yeah, let's say that. And so there's actually fewer curves, but somehow this Hamiltonian Flower Homology, because there's fewer curves, there's sort of fewer differentials for this Hamiltonian Flower Homology. So somehow you actually get more orbits that are sort of remembered somehow. So usually when there's fewer orbits is because there's lots of curves sort of cancelling everything out.
In the general type case, might it not be reasonable to not just study genus 0 J-homomorphic curves, but try to do something with
higher genus
going off with invariants? Because you expect that you have a lot of them, a lot of higher genus curves.
You expect to have a lot of high genus curves, but the problem is I don't know if Gromov invariants sees much of that. There's theorems which say that sort of a lot of that sort of disappears sadly and becomes much more difficult. That's probably why I'm looking at rational curves.
But specifically on complex surfaces, there's the top there relates Gromov Witten invariants to Seibert Witten invariants, and it's actually in the general type case where the Seibert Witten invariants are very rich. They're trivial for rational surfaces or for things that are dimension minus infinity. Right. So it might just, but those are great Gromov Witten invariants that involve higher genus curves.
Okay, so maybe there is some things to be said there.
So the sort of key example would be that the canonical class is represented by a J-homomorphic curve.
So I don't know in high dimensions what people know about this kind of thing. But would be
Any more questions? Not, let's thank Mark again. Will be a dinner.
I would like one comment. I thought that was a beautiful example of selecting understandable statements from a very complex field for the general audience. Give you a model.
The comment
He
is
selected
accepted for the record.
He did a lot of selecting. Well, there's an idea here. So he selected it a certain way. Communicable diseases or thoughts.
So anyways, there will be a dinner when you can make further comments. Ask Paul if you're interested. Thank you.